We've been talking about functions, and in this lesson, starting with page 12 in your notes, section 7.7, we're going to continue talking about functions, but now we're going to combine functions with inverses. So we're going to do a quick review of inverses before we jump into that combination. Remember that an inverse operation is something which undoes something else. Okay, something that undoes another operation. We talked about how, for example, addition undoes subtraction, how those two are inverses, how multiplication undoes division. They're also inverses. And we said every mathematical operation has an inverse. We talked about two special types of inverses. Remember, we talked about opposites and we talked about reciprocals. So just as a quick reminder for us here, when you combine opposites like 4 plus its opposite, which is negative 4, you get 0. When you combine negative 2/3 plus its opposite, positive 2/3, you get 0. And if we combine this with the opposite of positive 3 minus a, we would also get 0. And then when we combine reciprocals, this is where we would have 1 over 4. So 4 times 1 over 4 gives us 1. Or for this one here, we'd have 3 over 2. So negative 2/3 times negative 3 over 2. We'd get negative times negative is positive. The 3's cancel, the 2's cancel, we get 1. And for this one, we'd have 1 over negative 3 plus a times, we still get 1. Okay, so those are two special types. We also talked about PEMDAS. And we said how in PEMDAS, these two here, multiplication, division, undo each other, and addition, subtraction undo each other. And when you're solving for something, you undo multiplication with division. So what does this mean for us with functions? Well, go to page 13. So when we talk about inverses with functions, the definition of an inverse we said was something that undoes. For us, this means that we're going to swap x and y. Swap the x and the y values. So for example, here's a relationship, and you can see its domain here, and you can see its range. What an inverse does is it takes that range of the relationship and turns it into the domain of the inverse. And it takes the domain right here and turns it into the range. Okay, same numbers, but they flip-flop their positions. We're going to take a look at this numerically and graphically. So here, for example, is a relationship M with its x and its y values. To do the inverse, all the y values become our x values. So negative 5, 12, 13. And all the x values become y's. Negative 1, 0, 1, and 2. And we're going to graph these on the same graph together. We're going to go ahead and keep the inverse in red. So negative 5, comma, negative 1. Negative 5, comma, 0. 12, comma, 1. 7, 8, 9, 10, 11, 12, comma, 1. And 13, comma, 2. To graph the relationship here, M in blue, we have negative 1, 1, 2, 3, 4, negative 5, 0, comma, negative 5, and then 1, comma, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 2, comma, 13. So the blue dots are the original relation M, and the red dots are the inverse. Now, how does the line y equals x relate to the graphs of M, that's in blue, and its inverse, which is in red? Now, first of all, this line y equals x. The line y equals x, this guy here, is a diagonal line. It goes through the origin, and it comes directly out of this corner. It's a perfect 45 degrees. That is the line y equals x. Now, to talk about how do the red and the blue dots show a relationship around this green line, well, maybe you can already see it. This blue dot right here, for example, this is the point 0, -5. And then this red dot over here is the dot -5, 0. Notice how these two dots here and here are mirror images across this line. And these two dots here are also mirror images. We have this point up here and this point out here. This is the point 13, 2, and this is the point 2, 13. They are mirrored across this line, or reflected is the other word. So this line will say all points, all blue points, or all M points are reflected across y equals x to give the inverse points. That's what happens in this graph. Now, is the relation M a function? We can look at the graph and do a vertical line test. Remember, M is the blue dots, so think about a vertical line for all these blue dots. Is that okay? Looks like it's good, yep. We could also look up here at the graph and say, does every x have a unique y? So this x only appears once, only appears once, only appears once, only appears once. So yes, the relation M is a function. Now, is the inverse of M a function? Do a vertical line test. Oh, look. Vertical line test, we hit these 2 points right here at the same time, so that's not a function. Take a look at your chart. You have -5 going to -1 and -5 going to 0, so that's definitely not a function. We say no. So the original was, the inverse is not. Scroll back up to the top of your page. Let's take a look at what we see up here. In our mapping diagram, is the relationship R a function? So 1.2 and 1.4 share a birthday. 1.6 and 1.9 share a birthday, or again a range. So this is a function, yes. What about this one? No, the 1 splits and the 2 splits, so no. So that's interesting. We'll keep that in mind. Let's see if we can ever find a function whose inverse is also a function. We're going to keep an eye out for that. So there's lots of different ways we talk about. We have our rule of 4. So we said that an inverse swaps x and y numerically. That's what we just saw with the number chart or with the mapping diagrams. So we've done that. Graphically, we reflect all points about the line y equals x. We saw that a little bit. We'll come back to it even more. What we're going to focus on here is algebraically. When you swap x and y, but then you solve for y. So take a look at example 2. Algebraically, find the inverse of y equals x squared minus 7. And then we're going to show that both are inverses numerically. So for y equals x squared minus 7, the first thing you start with is to swap x and y. So you put x in place of y and y in place of x. And all the other pieces remain the same. Do not change your signs. Do not make this a positive. Don't do anything else, just the x and y. Once you have that, that's step 1. Now we solve for y. So to get this guy here by itself, we'll add 7 to both sides. So we have y squared. We need to get y by itself, so how do we undo a squared? We undo a squared by putting in a square root. And whenever we do a square root, we have to remember to stick in a little plus minus here. We'll talk more about why that is later. But for right now, just know that it's super important for us that when we use a square root to solve, place a plus minus in front. Okay, that's something we always have to make sure we do. So the square root and the squared are going to cancel, so we get plus or minus the square root of x plus 7 equals y. This is the inverse. Now it wants us to show that both are inverses numerically. That means do a number table chart. So we'll go ahead and we'll do a chart here and a chart here. And we'll go ahead and we'll put x and we'll put y and we'll put x and we'll put y. We'll say that this is the original and this is the inverse. So for the original, let's go ahead and let's say that we plug in numbers like, let's say we plug in the number 3. And let's go ahead and plug in the number 4 and 5 and 0. So when we plug in 3 to the original equation, 3 squared is 9, 9 minus 7 is 2. Plug in a 4, 4 squared is 16, 16 minus 7 is 9. 5, 5 squared is 25, minus 7 is 18. Plug in a 0, which is 0 squared is just 0, so negative 7. Over here on the inverse side, what do we have over here? Well, if we go ahead and we plug in, hopefully these numbers should all work, right? Because again, we expect that all of the ranges should become our domain values. And then we're hoping that all the domain values are what show up over here for our range values. So let's go ahead and let's use these same numbers in green, 2, 9, 18, negative 7, and hopefully what will show up will be the yellow numbers. So plug in a 2. 2 plus 7 is 9. Square root of 9 is 3. Now we do have that plus or minus out in front here. We'll talk about him later. But do we have a positive 3 over here? Yes. Plug in a 9. 9 plus 7 is 16. Square root of 16 is 4. Yep. 18. 18 plus 7 is 25. Square root of 25 is 5. Plug in a negative 7. Negative 7 plus 7 is 0. Square root of 0 is 0. So look at that. The numbers show up. So we just showed numerically that this is the inverse of that one. All right, here's another example, algebraically. And the reason we have to do this one algebraically is because it says graph y equals 3x minus 6 and its inverse. And then it asks us to say, is the inverse a function? So let's swap x and y, first of all. So x and y. Remember, leave everything else the same, so equals 3y minus 6. Solve for y. So add 6 to both sides. X plus 6 equals 3y. Divide both sides by 3. So we get 1/3 x plus 6 over 3y, which is the same as 1/3 x plus 2 equals y. That's the inverse. All right, we're going to graph the original in blue, and then we're going to go ahead and we're going to graph the inverse in red. So remember what we know about graphing lines. This is your slope right here, and this is your y-intercept at the back. So start with your y-intercept, negative 6. 1, 2, 3, 4, 5, negative 6. There it is. And then your slope is 3. So up 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 2, 3 over 1. So this is the original. And then to do our inverse, here's our y-intercept, the 2, and then our slope, 1/3. So y-intercept at 2, slope of up 1 over 3, up 1 over 3, up 1 over 3. There we go. That's the inverse. And then it asks us, is the inverse a function? So do a vertical line test with this red. Yeah, look at that. Vertical line would be totally fine all the way across. So is the inverse a function? Yes, it is. Now, notice too about inverses. What did we see before when we graphed? We said that dotted line, y equals x, was a mirror or a reflection line for our inverses. Look at how the blue one reflects across to the red line all the way across this green thing. So that's what inverses should always look like when you graph them. They should look like reflections of each other. Here's another example for us. Graph y equals negative x squared plus 5 and its inverse. So here's the original. Let's do the inverse. X and y equals negative y squared plus 5. So subtract 5. We need to get rid of that negative, so we'll multiply both sides by a negative 1. So this becomes negative x plus 5, and this becomes y squared. We need to undo that squared, so we're going to slip in a square root and a square root. Remember, whenever we do a square root, we need that plus minus. So negative x plus 5 equals y. This is our inverse. Now, we're supposed to graph both of these. Graphing our first one here in blue. This one is going to be something that we might need to do with your graphing calculator. So if you go to your graphing calculator, go to your y equals button, and go ahead and type in this equation here, and then make sure that you hit graph, which is also at the top of your graphing calculator. If your picture looks funny and you can't see what I'm about to graph here, then you might need to hit your zoom key and go down to hit number 6, and that'll make your picture show up a little better. If you still have questions on the calculator, make sure you ask me after this lesson. So this blue one here, if I'm looking at my graphing calculator, this one's 1, 2, 3, 4, it's 5 up, and it's also going to be facing downwards, kind of like that. And then the red one, on our graphing calculator, this one's going to be kind of funny to graph. When you go into your y equals key, you see lots of different options like y1 equals and y2 equals. We have to graph two separate things because there's a plus 1 and a minus 1. Your calculator does not have a symbol for this, so we have to do this by hand. And what we're going to do is we're going to go ahead and do a square root of negative x plus 5 in your graphing calculator, and then do a negative square root of negative x plus 5. That's how you get the plus and the minus to show up together. Your graphing calculator then will take this and it will graph something that looks like that. That's what it should graph for your inverse. So as we're looking at these, is the inverse a function? And I hope you can tell right away as you're looking at it, no, the inverse is not a function, because look at this, it fails the vertical line test. It hits it twice, there and there. Now, remember what we said about graphing and inverses? They should be reflecting about this diagonal line here and here. And sure enough, if you check your screen, you can see how this point right here, this on your screen should be the point 5, 0. And if you check this point up here, that's going to be the point 0, 5. The numbers flip-flopped and they are reflected across. And notice each piece of the blue graph is reflected across for the red graph. And even this long arm down here comes along across, crosses over. This long arm here comes along, crosses over. Everything should look reflected for these graphs. So we've seen a couple examples of getting inverses from functions. And one of the things we want to say is that every single function has an inverse. No matter what, every function has an inverse. But we just saw an example up here with this red one. That inverse is not a function. So not all inverses are functions. Some are, but not all of them. So for example, we could say inverse is a function. Look at these examples, and inverse is not a function. So example 4 is where there's not a function, but the one right above that, example 3, is a function. Okay. The definition of an inverse function is that the inverse also has only one y value for each x value. Only one y value for each x value. So it's the same definition as you have for a function. We're just saying that the inverse also has it. When we do talk about inverse functions, we use this special notation. This here, I know it looks like an exponent. It is not. Not an exponent. It is a special way in math that we say inverse. So whenever you see this little -1 way up top there, it should just mean inverse to you. Okay? Just a code word that we use in math. All right, last couple examples here is we have some graphs, and we want to find the inverse of each graph. Now remember we said for graphs that they should reflect across that y equals x line. So you need to think about drawing in that y equals x line. Remember it starts at the origin, just goes out at 45 degrees for each of these graphs. And after you have your y equals x line on here for this, then we're going to go ahead and reflect. So think about this point here. On your graph, that is the point 0, 3. So we need to flip it and make it 3, 0. 1, 2, 3, 0. This is the point 1, 0. So we need to make it the point 0, 1. And we saw that this connected to here on the original. So we're going to connect this to this one. The next point was 2, 1. So we need the point 1, 2. Connect. This point here is 3, 0. So 0, 3. And then lastly, this is the point 4, 3. So we need the point 3, 4. Okay, so you can do it by looking at the points, or you might just be able to look at it and say, oh look, I see that this looks like a mirror, like they're reflected around each other. There's this long arm here, there's a long arm here. Then it kind of juts inward, juts down, juts across. You might see it visually like that. Like for example, this one's kind of a visual one. Think about we're both starting here, but then what has to happen? I kind of have to loop, and then I kind of have to come in close, and then I kind of have to come back out at the end. And that's a rough sketch, but that's a basic reflection of this shape. Here's another one where it would be good to do that. You're starting at the origin here, and see how there's a loop that comes down here? I need to have a loop that also reflects across this green line here. I have this arm that sticks out, so I'm going to stick an arm out here. And I'm going to, there you go. So this long line comes down, this long red line comes out like this. This line comes out here, I'm going to reflect it out, and then there's this piece here. Okay, so this blue line here looks reflected with this red line across the green. This one, it's going to share this piece here, so that stays the same. And then this piece has to come out at a 45-degree angle. Last two here to finish up for us. This one's going to reflect out that way. This is going to have to kind of like that, sort of. And then this one here, this one's a nice one. This one's going to start, and we're going to curve it like this, cross, cross again.